Derive the Bernoulli equation. This is a formal example, and I'm going to use the answer that's in the slide. It's going to come out in multiple parts. And as I go through, I'd like to record what happens on the board so that by the end we have the full derivation up on the board. So let's go ahead and get started here. Here is the Bernoulli tube. It will let us look at some fluid moving along a flow line. Now, the Bernoulli tube is something I just made up for this derivation. So don't go and Google the Bernoulli tube. Or if you do and you find out there's already something called the Bernoulli tube that I'm not aware of, maybe let me know that I am using an idea in the wrong way. But as far as I know, I made this up just for this derivation. The Bernoulli tube represents a change in pressure, flow speed, and height. In reality, these changes are more continuous, but here they occur rapidly in one step on the flow line the tube represents. So if you look at this tube, right, there is this kind of bend here. It happens pretty quickly or in a short horizontal space. And it really represents how on one side there's a pressure P1, flow speed V1, and height Y1. And on the other side there's pressure P2, flow speed V2, and height Y2. And Y1 and Y2 are both measured in relation to a reference height that kind of represents what 0 would be for that height. And so really it's the vertical arrow that represents respectively the Y1 and the Y2. Let me go ahead and start to bring this into the whiteboard here. And to help me out, I pre-drew a version of the Bernoulli tube because I kind of thought I would take a while to draw it during the recording. So I did that ahead of time. And then let me label in some of these other things, like these quantities like the pressure, or pressure since we got P1 and P2, the flow speeds, V1 and V2, and then we also have the heights, and so I can kind of draw here maybe that 0 height line and an arrow for Y1 and another arrow slightly longer for Y2. Now it said here that in reality these kinds of changes would happen more continuously, but one way to imagine this is to say, well, how could this be a model for part of that reality? What if we broke up a continuous change into many small steps like this, and if we can show that the Bernoulli equation holds for one of the steps, then it might also hold for the whole continuous change or for any arbitrary point along a set of continuous changes. So that's the argument I'd like to make that validates what we're doing here by kind of putting this change all in one sort of rapid bend in the tube, or that really represents the flow line the fluid is flowing along. The fluid is regarded as having constant density, so we can put in labels here for density and say it's the same density rho on both sides of the bend because the fluid is incompressible would be another way to say it, because that means it's going to have constant density. It says here, if this were not the case, thermal energy changes associated with the change in volume of the fluid would have to be tracked, since it would likely not be isothermal. So what that has to do with is that in reality, if you compress or expand a fluid, there tend to be changes in temperature associated with that, and those changes in temperature correspond to changes in thermal energy, which is really can be regarded as a change in the internal energy of the fluid if it's compressible. And that winds up spoiling the whole result of the Bernoulli equation. So we have to assume that there is no energy going into or out of the fluid's internal energy, and that corresponds to the assumption of incompressibility or constant density. So, all right, let's move on. Consider a long section of fluid moving through the tube. Note that it is long compared to the region of change so that work done to it as it goes through can be tracked. So it doesn't really matter how long it is, but my intention is that it is longer than, by a significant amount, than that bend that happens in a relatively short distance there. So the length should correspond to a much greater distance, moreover. Um, and in a moment, we're going to look at how that relates to figuring out the work as it mentions here. But part of the issue is going to be is establishing how much displacement happens as this long section of fluid is kind of snaking through this bend here. And being able to say with some certainty in an expression like what is the displacement for that. It's going to actually correspond to the length of the section of fluid. If the section of fluid were short, then you can kind of arbitrarily set the displacement, and if you know what you're doing, you'll get the correct answer. But if you chose maybe the wrong size, or thought about the size of the bend too much, you might wind up spoiling the answer. So I prefer to not do it that way. It says here the long section of fluid will fully go through the place in the tube where the pressure, that's the place I was talking about there, is that bend, where the pressure, flow speed, and height all change. And we're going to use W equals delta E. In other words, work is equal to change in energy. Maybe a tacit assumption there is work is equal to change in mechanical energy, since we've already said no thermal energy changes are allowed due to incompressibility, right? Will be used to analyze this process. So let me add that to my picture up here. So somewhere I want to add, try to make it about the same length as the other side. Maybe draw it similarly. I know I'm not going to get identical though, because yeah, okay, that's going to have to be good enough. Okay, so there it is on the other side. Oh, and before I move on, I was about to move on, and I'd like to write down W equals delta E, because that's what we said we're going to use. So I'm going to regard that as the starting point for my derivation. The section of fluid that is the system has a length delta X and cross-sectional area A. So let me see. I think I can squeeze that in here. One of the issues that happens with on the board is the more symbols you add, the more complicated it starts to look. And that's why in the slides I broke things up a little bit so that we could see things separately as they got added. And hopefully we can remember as we add them to the board so that later on it will all make sense. When you just look at it when it's all done, sometimes it's really hard to make sense with these kinds of sketches for derivations. The initial state, it says on the slide, should be clearly defined. So this is in general a good idea anytime you apply a formula like W equals delta E. It also applies if you're doing energy conservation, but we definitely want work here. We're going to have work done to this system, but it's always a good idea to define clearly what is the initial state, and it's also a good idea to define what the final state. So we're going to add the final state. That might not be too much of a surprise since we've already kind of drawn these two parts, that those are going to be the initial and final states that I'm going to consider in looking at W equals delta E, particularly for the delta E side. That's going to be important. Now the slide is taking us to the work done side to figure out an expression for that here. It says the work done is based on forces due to the pressures and the displacement. So I want to draw maybe a separate picture for this. And I'm just going to freehand this one here, so it may not be good. I always put that warning out there because freehanding, I don't know, I have a hard time. So let's say there's this fluid going through the bend. Part of the argument here is that there's really only a non-zero net force on this section of fluid when it's going through the bend, because everywhere else, like when it's not in the bend, like in the initial and the final states pictured in the sketch up here still, there the pressure is P1 on both sides and balances out. Pressure really balances out on all sides there. So the net force is equal to 0. But when it's in this bend, there's a pressure P1 on one side and a pressure P2 on the other side, right? So there's kind of a P1. I'll just put that over here. There's a P1 being applied right there, and there's a P2 being applied right there. They're both being applied to the area A of this section of fluid. And since the pressure P1 is kind of applying force to the back of this section of fluid, if I were to draw an FBD for this, I could associate a force F1 that would point in the right direction. And for P2, I could associate a force in the opposite direction, since P2 is kind of the pressure in front of the fluid. That's pushing back, right? So that's going to point to the left, so with a force F2. And F1 is going to be equal to P1 times A, pressure times area. Force is pressure times area. And F2 in turn is going to be P2 times A. And so what this does right here, maybe what we can put up here in our derivation is I'm going to argue that the work really corresponds to the net force, in this case, due to those pressures, times the displacement delta x. And kind of based on what happens here, I don't know if I want to put in all those steps there. I mean, maybe I can. That net force should be F1 minus F2. And you can see that also from that free body diagram, because F1 pointing to the right, that's the positive direction conventionally, and F2 pointing to the left is the negative direction conventionally, so that makes sense. And maybe I'll skip a step here, because you can see what happens is, since both of these are a pressure times an area and it's the same area, we can factor that area out and just turn this into P1 minus P2 times A delta x. But really that's going to be P1 minus P2 times the volume. And let me make that volume V nice and large, because we also have flow speeds V1 and V2 that are going to come in. So let me throw in some equal signs here, because we've been kind of just working vertically the work side of W equals delta E. And the next thing we're going to do, I might need to create some space for it, is we're going to do the delta E side. So let's move on and do that. So that's what's now on the slide there. The energy change is given there. And like I said, I feel like I need a little bit of space. So I'm going to take all this stuff and maybe kind of move it up here into the corner. Okay, to give us some more room to write what we have on the slide here. So the first part is pretty clear, I think. You can separate the change in mechanical energy to a change in kinetic energy plus a change in potential energy, and that's really gravitational potential energy. So if you wanted to put a subscript G for gravitational potential energy change, you could do that. And then the change in energy in general is going to be final minus initial. So these labels of final and initial that on the slide have also come back here are meant to help us figure this out. And so in general, we can say, okay, if the 2 side represents final, then for kinetic energy, it's going to be 1/2 mv2 squared minus 1/2 mv1 squared. And then for the change in gravitational energy, and this is where I'm going to hope I don't run out of room, mgy2 minus mgy1. Okay, that one I got to squeeze a little bit, I think, in there. The next step that is there on the slide changes all these masses to the density times the volume that is there. So I'm going to do that for each one. This is where I might run out of space. And I'm not sure if my 2 sides here are lined up the way I want them to be either, because I'd like to eventually be able to do something with all these volumes that now appear on both sides, but I haven't quite lined them up vertically is the issue for me. Okay, that's okay though. Okay, and then here we have rho volume Gy2 minus rho volume Gy1 can barely fit in there. Okay, so what we have here, there's kind of a summary here that this is what I meant by things are not quite lined up, because if you look at this equation here, P1 minus P2 V is equal to all this stuff. That's what I have here, and I had this on the next line. Maybe what I can do though is I will just, oops, hopefully I didn't miss any part of it there. I'm just going to copy that and then maybe just double check that I didn't miss any part of it on the next line, because that's faster than me writing it again. And then we can cancel all the volumes. So, oops, I turned pen mode back on. Okay, so we're going to cancel all these volumes out. And then what remains is, is P1 minus P2 equals 1/2 rho V2 squared minus 1/2 rho V1 squared plus rho G Y2 minus rho G Y1. And what we can do with this is we can take all the negative parts and add them to the opposite side. So that means P2 will go to the right, and the minus 1/2 rho V1 squared and the minus rho GY1 will get added to the left side, and that gives us the overall result that we've been waiting for. And hopefully you'll be patient to let me finish writing this, or if you're fine, you can maybe move on at this point since you can see what I'm going to write down, right? But I just want to finish what I have on the board here. And this is the equation that was there at the top on the key concept slide. And then the second version of it was basically saying, well, if you can say that 0.1 in terms of this expression and these quantities is equivalent to what this expression would say for a 0.2, and then maybe there could also be a 0.3 or a 0.4 and so on and so forth. In that sense, maybe you could take like a continuous change and subdivide it into a whole bunch of little bends and have like an infinite number of points, all where pressure plus 1/2 density times flow speed squared plus density times g times height would be the same for all of those points. Well, that really means that expression is a constant, and that was the other version of the Bernoulli equation that we had.